So to understand the properties of a determinant related to the columns of a matrix, we need to understand this geometric interpretation of the determinant. So let's say that a matrix A is a 3 by 3 matrix given by 3 column vectors, A, B, and C. Now remember what the columns of a matrix meant, yeah? So remember that if you have a linear transformation where a vector V ends up as a vector A times V, what happens to x hat? X hat ends up as the first column of the matrix A. So that would be A. Y hat would end up as B, and Z hat would end up as C. Yeah. Therefore, a unit volume in the input space, which has x hat, y hat, and z hat as the different sides, would end up as a volume given as the parallelepiped formed by the 3 vectors A, B, and C. So A, B, and C. This would form some sort of volume. And that volume, so since the volume of the initial square of sides 1 was 1, the volume of this parallelepiped would be the determinant of the matrix. Yes? And this is what I'm showing here on the right. So here I'm showing the 3 columns of the matrix, A, B, and C. And I'm saying that the volume of this parallelepiped, yeah, that's the name that this figure is given, is equal to the determinant of A. Okay? Now, the sign of the determinant depends on whether A, B, and C form a right-handed triplet, so A cross B is in the direction of C, or if it's a left-handed triplet, so if A cross B is in the direction of C, then it will be a negative determinant. Okay? But this means that we can say several things about the determinant just by looking at the columns. And for that I have prepared an applet, so let's have a look. So you can see it here. So here I have the 3 columns, A, B, and C, as the 3 vectors. And I'm plotting the volume that they define. Yeah. So first of all, what would happen if one of the columns, for example, the blue arrow, column C, is a linear combination of the other 2, which means that this blue arrow is in the plane formed by the other 2. So then what happens is that the volume goes to 0 because the 3 vectors are on the same plane. Yeah? So if the volume goes to 0, the determinant is 0. Therefore, we can write a property as follows. If the columns of a matrix are linearly dependent, then the determinant is 0. If the columns of a matrix are linearly dependent, the determinant is 0. And the reason is that the 3 vectors lie on the same plane. Or if we were looking at a 2 by 2 matrix, then the 2 vectors are in the same line, they are parallel to each other. Or if we were looking at higher dimensions, 4 by 4, 5 by 5, then we cannot picture it, but the idea is the same, that the volume, the n-dimensional volume would be 0, because the vectors are linearly dependent. So that's the first property that you can tell a determinant just by looking at the columns. The second property is that if you interchange any of the 2 columns in the matrix, this flips the sign of the determinant because you are changing the right-hand triplet into a left-hand triplet. Okay, so let me write it here. Okay, so basically if the determinant was 4, it becomes -4. Yes? So the magnitude is unchanged. And that's because the volume formed by the vectors is the same. If we change, for example, A with C, we swap them, the volume is the same. It's just that the handedness of the volume changes, so the sign changes. Okay, and then the third very important property. Let me first write it and then I explain it. You can add to any column a linear combination of the other columns, and the determinant is unchanged. And let me explain it with symbols or with writing the matrix. So the determinant of a matrix formed by 3 columns, A, B, and C. This would be equal to the determinant when we choose one of the columns, for example, let's choose the second column. So we leave the first column unchanged and the third column also unchanged. But in the second column, we get B, but we add a linear combination of the other two. For example, half times A minus 100 times C. Okay, so that's a linear combination of the other two columns. We add it to column B, and then we leave column C as it is. So these two determinants are equal. Okay. Let me show you from the properties that we showed above that the determinant is linear in the columns. We can prove it, right? So prove using linearity in columns. So we know that this determinant here can be written as the linear combination of this one plus 1/2 times the determinant of this one minus 100 times the determinant of this one, C. Right? So remember, we can apply linearity to the columns of the matrix. That was one of the properties that we saw previously. And now look at this. So this determinant has two columns that are the same, and therefore the volume of the parallelepiped is 0, so this goes to 0. And this determinant also has two columns that are the same. So the volume of the parallelepiped, so the determinant is 0. And therefore we have proved that this determinant here on the right is equal to this one, which is this one on the left. Okay? So that would be the proof. I can also give you a visual proof. So let's go back to the screen share, to this applet. So we have three vectors, yeah? So let's say that the three vectors start as independent from each other. So let me make them independent of each other. So they form right angles with each other, okay? So we have like a cuboid, and the volume of this cuboid is just the length of each of the vectors. Now to the blue vector, I'm going to add a linear combination of the red vector. So I'm going to add, you notice that I'm moving the tip of the blue arrow, I'm moving it in the direction of the red arrow. So I'm adding to the blue vector a linear combination of the red vector. So does the volume change? Does the volume change when I do this? The volume doesn't change, okay? Because this is a shear. This is a shear of the volume, and the volumes do not change when you shear them. So let me draw this on. So remember, if you have an area that is a rectangle, for example, this is an area A. If you get the sidewall and you move it to the right so that it becomes like this, but with the same height, yeah? So the resulting area, which in 2 dimensions is called a parallelogram, so this resulting area is equal to the area before the shear. Yeah? So shears do not change the areas of an area, or do not change the volumes of a parallelepiped. Yeah? So this means that we can indeed add any linear combination of the other vectors to the blue vector. So we could add linear combinations of the red vector, or even linear combinations of the green vector, moving it in the other direction. Yeah? And this doesn't change the volume of the parallelepiped that is formed. Okay? So with this example, I hope you understood this third property that I wrote here. That you can add a linear combination of columns into any other column, and the determinant is unchanged. By the way, every single property of the columns also applies to the rows. Why? Because if you remember, the determinant of A transpose is equal to the determinant of A. So whatever we say about the columns of a matrix, we can also say about the rows of a matrix. Yeah. So all of these three things we could substitute. If the columns are linearly dependent, the determinant is 0. This is also true for the rows. The second one, interchanging any two columns flips the sign. This can also be said about the rows. Interchanging any two rows flips the sign. And finally, you can add to any row a linear combination of the other rows, and the determinant is unchanged. Okay, we can say those two. So with this, we finished with 2.1. So see you in the live session, and we can discuss any questions you have. Thanks for watching.